Welcome to the course module of Communication Engineering. So in the last lecture, we have seen the time division multiplexing. Now today we are going to start one more topic, whose name is digital modulation schemes. So let's begin the discussion. So in digital modulation scheme, which is also known as the band pass data transmission, so that we have to study today, okay, in this particular lecture. So let's try to understand that what is this digital modulation scheme and how it is actually being implemented in real life. So as I said, in the case of pulse code modulation, if you remember that while having an analog signal, we converted it into a digital signal, and after performing the encoding of the signal, the encoded binary bits were launched into the transmission lines, okay, by having an appropriate line codes, okay. So I already explained you about line codes such as polar line coding, bipolar, Manchester coding, okay, in which we have already seen what is written to zero and what is non-written to zero line codes. So that line codes are generally used, and then the corresponding waveforms is actually being launched into a transmission cables, okay. And those transmission cables are nothing but our like twisted pair cables. It may be a coaxial cables, okay. It may be a fiber optical cables. So basically those are the wired media, okay. Those are the very basically wired media, and they are also referred as the baseband channels, okay. Because when we send the signal, that signal is actually taking a low frequency component. So if you remember that I explained you about the rectangular pulse, and the rectangular pulse, its Fourier transform is the sinc function, and basically this sinc function was actually varying from 0 to 1 upon TB, okay. If you remember, its major lobe. So basically that particular portion is actually taken for calculating the bandwidth requirement. So basically these pulses are actually containing the basic low frequency components, okay, when we reject all other high frequency component, and therefore it is referred as like a baseband signal, and we use the band pass baseband channel, like wired channel, for transmission of this particular signal. Now let's assume that if we want to send the same signal, okay, through a band pass channel, okay, I mean to say that it may be like our wireless channel. So if we want to send the same thing using the radio links, okay, so if we have a transmitter, and if we want to convert the signal into a electromagnetic wave, and then we want to send it through the wireless channel, and then we want to receive it. So if you recall my first lecture, I told you that what is the basic requirement of transmission through a particular antenna is the height of the antenna, because height of the antenna does depend on the message frequency, okay. And whenever we have the low message frequencies, or significantly low frequency component, that time the height of the antenna is not practically realizable. So what we do is we generally multiply the our baseband signal with a very high frequency carrier, and because of the multiplication with the carrier, the spectrum of the baseband signal is actually shifted to a high frequency region, and that particular spectrum can easily be sent by using the transmitter, because the height of the transmitter is physically realizable. The same concept we are actually also using in the case of digital modulation scheme, okay, which is also called as the band pass data transmission scheme. So in this, again, what we do is, if you try to understand the basic differences, here the message signal that we are going to multiply with the high frequency carrier or sinusoidal carrier is our digital data, okay. You remember that it will be a digital data, fine. But in case of analog modulation, if you remember, we used to have a analog message signal MT. So that message signal MT was actually multiplied with the carrier CT, and then a frequency translation was occurred, okay. And thereby we have shifted the low frequency component to high frequency component, and then it was sent through the particular antenna over a wireless medium. Now here just the only thing that we have to understand is we have to take the very high frequency carrier, sinusoidal carrier, and then this carrier has to be actually multiplied with the this particular digital data stream. Okay, so once we have generated the binary bit like 10110001 for a particular sample, then this binary bit has to be converted to a particular line codes. Okay, so here we can see that we are having a line code corresponding to this binary data. Okay, so now after having this line codes, this has to be multiplied with the carrier, okay, of a certain frequency, and then this type of waveform is going to be generated. Okay, so here we can see that this carrier is actually being multiplied with this digital data, okay, particularly this waveform. Okay, and then this type of output we are going to get. Okay, so in this region we are going to get a certain this type of sinusoidal carrier, okay, for a certain duration. So let's say that this duration is of TB. Let us say this bit duration is equals to TB. Then for this TB duration, we are going to get the carrier of a certain frequency and certain amplitude. Now, whenever it is zero, you can see that if we multiply zero with anything, then and that becomes zero. So again, for the next duration of TB, the absence of the sinusoidal carrier will take place. So similarly, again, wherever it is one, based on the digital data, we are going to get the certain output. Okay, certain carrier we are going to get. Now you try to understand this, okay, because in case of analog modulation, we have seen like amplitude modulation, we have seen frequency modulation, phase modulation. Okay, in a similar fashion, again we are going to get this three type of digital modulation schemes also. For example, here we can have like amplitude shift king. Okay, another name means amplitude shift king. Then we are having phase shift king, PSK. Okay, and then we are having frequency shift king. Okay, so here we can see that if we have this type of data, you remember that this is a non-return to zero type bipolar signaling, we can see. Okay, it is having a bipolar signaling, polar signaling, you can say. It is non-return to zero. So in this format, if you see, if we multiply with this carrier, wherever it is plus one, it is going to have a certain carrier, okay, at this point. Okay, and whenever it is multiplied with the minus one, there will be a phase reversal of this carrier will take place. So that phase reversal you can observe at this particular point. So what we can understand from this output here is that whenever this bit is equals to 1, a carrier will be sent, and whenever there is a 0, a carrier again will be sent, but there will be a 180-degree phase shift. Okay, so here it is a 180-degree phase shift that we can observe in this particular waveform. So that we have to observe in the case of our digital carrier modulation schemes. Similarly, this will be called as like phase shift king, because we are actually means try to embed the message into the changes into the phase of the carrier. Okay, so basically what we are modulating is we are modulating the phase part of our carrier. Here we have just modulated the amplitude part. Here you can see that wherever there is one, so this carrier is present, and then whenever it is zero, this carrier is absent. So basically based on the amplitude of this waveform, the amplitude of this carrier is going to be decided. But here in this case, based on the amplitude of the message signal, the phase is going to be decided, and therefore we are saying that it is a phase shift key. Okay, similarly here you can find that we have two different frequencies. Okay, like here we are having a certain frequency of the carrier whenever we are having bit 1, binary bit 1, and whenever we have binary bit equals to 0, we are having another carrier frequency. Okay, another carrier frequency. So basically we are going to have two different carrier frequencies, okay, that will be sent, one for binary bit 1 and another will be sent for the binary bit 0, and thereby we can have a frequency shifting. Okay, because this amplitude is going to modulate the frequency of the carrier. And this way we can have different modulation schemes such as the ASK, which is amplitude shift king, PSK, phase shift king, and FSK, which is your frequency shift king. So this way we are having a digital carrier modulated signal, and now this particular waveforms will be actually launched to our antenna, and this antenna will be radiating this through an electromagnetic wave, and it will be sent over the wireless channel, and then at the end of the receiver, and this signal will be obviously attenuated, or it may be deteriorated, or you can say there may be a certain distortion due to the presence of the channel noise, and then it will be received, and then a certain demodulation technique again we have to perform to get back the original message signal, or to decode the basic information available in this carrier. Okay, and then this way we can receive our original bit string. So to begin with this, what is amplitude shift king, what is phase shift king, let me start with one of the important topic, okay, and that will be used for discussion of this particular ASK, FSK, PSK, okay, while calculating the bit probability of error, okay, that discussion is actually required to try to understand the signal space representation or geometric representation of signals, okay. So try to understand what is this signal space representation. So basically in this case what happens is, let us suppose if we want to generate a certain signal, okay, if we want to generate any signal, so let's say that this signal whatever we want to generate is corresponding to our like band pass data transmission. We want to generate a certain digital modulation scheme, okay, it may be ASK, FSK, or it may be PSK, okay. So that signal we want to actually generate, okay, we want to generate. So that signal SIT, if I refer this as a SIT, so if we have any SIT, then this signal can be generated by having this particular equation, okay. Try to understand what this equation reflects here. So basically if you see this expression, we are having a certain amplitude factor which is Sij, and if this Sij is actually multiplied with a function of t like phi jt, okay. So here this phi jt is actually known as the basis function. You try to understand this particular terminology. So this is generally called as the basis function, and this basis function will have a certain amplitude Sij, okay. So if suppose we want to generate any signal, okay, so that signal maybe if we talk about like this number of signals that we want to generate is 1 to m, okay, number of different signals that we want to generate. So what is this 1 to m actually denotes is, it is denoting the number of message points, okay. If you are not able to exactly follow, do not bother, you will be able to understand at the next slide, okay, when I will start with the amplitude shift king. But a certain information you have to understand from this particular slide. So try to understand that this I actually reflects the number of message points that we have in the signal, okay, 1 to m, and that we want to generate for a duration of 0 to t, or you can say the bit duration tb, okay. And here we have another like factor j is equals to 1 to, like this summation is actually going over from j equals to 1 to capital N, where this 1 to n may be less than or equals to m. And generally this capital N or this gen is actually j actually reflects the number of basis functions that we are actually using for generation of this particular signal SIT, okay, number of basis function that we are actually using, okay. So how to calculate this Sij, okay, if we want to calculate this particular factor Sij, okay, this amplitude factor Sij, that can be calculated, this Sij can be calculated by integrating this signal SIT, because SIT is actually the linear combination of this all the basis functions with certain factor, okay. As I said that this is our basis function, okay, this is our basis function, and this is the coefficient of this basis function. So if we want to calculate this factor Sij, out of this SIT signal, okay, which is the summation of all this basis function with this particular coefficient. Then to calculate Sij, we can integrate it over 0 to t time, and then this SIT will be used. And then a certain basis function phi jt should be multiplied. And then if we integrate it over, we will be able to get a certain coefficient Sij. For example, if you see this same thing diagrammatically, okay, here we have the diagram. So what we are trying to say is that we are going to generate a certain signal, okay, and this signal SIT is actually being generated by having a certain amplitude factor like SI1, and it has been multiplied with the basis function phi1t. Similarly, we are having another amplitude SI2. This is actually multiplied with the basis function phi 2t, and similarly up to basis function n, capital N. So we are having a nth amplitude factor equals to SIN, and then after summing up all these inputs, we are able to generate this signal SIT. So once we have generated this, okay, generally this is called as the synthesis of the signal, okay, of this particular vectored signal, okay, this is called as the vectored signal. So basically these are the different vectors, okay, I will call it as a vectors. These are the basis functions because this particular basis function is actually having a certain mathematical properties, okay, and therefore this summation is actually a vectored summation, okay. But try to understand why it is vectored summations. So there will be a signal SIT that we will be generating. So after generating this SIT, and this is actually called as the synthesis of this particular signal. Now, if we want to calculate what is SIT out of this SIT signal, SI1, I mean to say SI1. So that can be calculated just by taking this signal and multiplying the same signal with the same basis function phi1t. So actually it has been multiplied here with the phi1t. The same phi1t has to be multiplied, and then we have to integrate it over a 0 to time, 0 to t time. So that will be giving you output equals to SI1. This is very important expression, okay? Very important expression. Here the same thing that we have written mathematically, the same thing actually shown here, okay, diagrammatically. So try to understand that we have to multiply with the same basis function, and then we will be able to get back this SI1. Similarly, to get the SI2, the same signal has to be multiplied with the phi 2t. Again, we have to go for the integration. And similarly, to get back the SIN, we can have this phi nt, and then we can get back the SIN. It means that whenever we are having such signals, okay, so any amplitude that we have multiplied to a certain basis function, then this amplitude can be actually recovered. You remember that, okay? This amplitude can be easily recovered by having this type of scheme, okay, by having this type of a scheme, okay. So that can give you this particular amplitude value. So this is what we actually perform in the case of ASK, PSK, FSK, that we have to look at, and then you will be able to understand the signal space representation. So here you remember that this basis function phi jt is a real valued orthonormal function, okay. So what is this orthonormal? So this word is actually combined word, okay. So it is means consist of orthogonality plus normalized function, okay. It is orthonormal means it is or orthogonal function, plus orthonormal means it is orthogonal function, and also it is a normalized function, okay. So here you can see that when it can be called as orthonormal and means orthogonal, and when it is called as the normalized function. So if you have this basis function of phi it and phi jt, okay, if we do this like integration over 0 to t, okay, then this is going to be delta ij. So what does it mean by delta ij? This reflects that whenever I equals to j, okay, I equals to j, that time you remember I equals to j means when we are having phi 1t multiplied with phi 1t, okay. If you integrate it, this results in value equals to unity, okay. So whenever it gives you unity, this integration gives you unity for I equals to j, for all the multiplication I equals to j, okay, whether it is 2, 2, 3, 3, 4, 4, n, okay, whatever. So this integration is going to give you this value equals to 1, and it will be like referred as a normalized function, okay, because this integration is equals to 1. Similarly, if I is not equals to j, if let us say I equals to 1 and j equals to 2, then all these basis functions are orthogonal to each other. And the meaning is, if you do this integration, okay, after multiplying phi 1t to phi 2t, then this integration results you equals to 0. Okay, it will be giving you this inner product, you can say, or you can say this integration that will be equals to 0. And that reflects that this all the basis functions are actually orthogonal to each other. So with this basic idea, okay, with this basic idea, we can start our discussion of amplitude shift keying. Okay, so let's see that what is this amplitude shift keying. Okay, so as I explained you that in the case of amplitude shift keying, first of all, everything we have to perform. For example, whatever we have done in the case of pulse code modulation, if you remember, we had to take the analog message signal, and then this message signal has to be converted into a digital signal, okay, by following the sampling process, quantization process, followed by the encoding. Okay, so once we generated the binary bit stream like this, okay, for a particular sample, then we have to actually generate a particular line codes. Okay, remember that here the line code that we have to generate for generation of the amplitude shift keying, okay, that should be an on off signaling. Okay, so it should be like here it is unipolar on off signaling we had to use. Okay, so this type of waveform, this type of line codes is only used, remember that. Okay, so it's not like polar signaling, it is just a unipolar signaling, okay, on off signaling that we have used. So in this case, whenever there is a binary bit 1, there will be a presence of pulse. Okay, whenever there is a binary bit 0, there will be an absence of pulse for the bit duration of TB. So this way we have to first generate the line codes, and this line codes will be applied to a product modulator. Fine. So after applying to this product modulator, we need to apply a certain carrier of a very high frequency. So as we know that once we multiply, we apply to this two things to the product modulator, the output will be the product. Okay. So you can see directly from this is whenever there is a binary bit equals to 1, okay, binary bit is equals to 1, that time the output will be in the same carrier. Okay, so this carrier will be S1T. So I will be calling this as S1T, the signal 1. Okay, this is our signal 1 corresponding to bit equals to 1. So that I will be calling it as like AC cos to pi FCT, and that will be actually generated for the duration of 0 to TB. Now next, whenever we are having next bit like equals to 0, for binary bit 0, I will be generating another signal, which is I will be calling it as S2T. That will be equals to 0 because it is multiplying with the 0 will give you 0. So here it is an absence of carrier. That will be represented by this particular equation, and again it will be generated for the duration of 0 to TB. Now, you think about it, okay? This is very simple to understand that if we multiply it, we are going to get this type of waveform, okay? Due to the nature of this particular line code, okay? Because it is 0 at this point. So wherever it is 0, the output should be 0. Now you try to calculate what will be the energy, okay, when we are sending this type of waveform. Okay, you remember that because this is a periodic signal, okay, it is a periodic sinusoidal carrier that we have taken, but when this periodic signal is of infinite duration, obviously it will comes under the class of power signal. If you recall my previous lectures, okay, because it is actually having the finite amplitude, but because its extension is up to infinity, okay, and therefore it will be comes under the power signal. Okay, but when we are restricting this repetition of our carrier, okay, to a certain amount of time, obviously it is going to be our energy signal because it is of finite duration. So now what we can calculate is we can calculate what will be the bit duration, means what will be the energy within one bit duration, okay, of this particular carrier. What will be the energy? So how to calculate the energy for any signal, if you remember? So within this bit duration, so I am calling it as a energy per bit, you can say that, or within this bit duration, EB, okay. So this EV can be calculated by integrating the signal, for example, S1t over minus infinity to infinity mod over S1t whole square dt. Okay. So this way we can calculate the energy, because the signal actually exists for the duration of TB. Okay, it can be integrated over 0 to TB, and then we can calculate what will be the value of EB. So here we have S1t equals to AC cos 2 pi FCT, so that you can substitute here, okay, AC cos 2 pi FCT. Then you can try to integrate it over, okay, and then you will find that this will give you results equals to AC square TB by 2. It is very simple to calculate, okay. So this is going to give you results equals to AC square TB by 2, okay. This will be the result while calculating this particular energy EB. So that from this discussion, you can see that AC equals to root over 2 EB by TB. Okay. So this AC we can substitute this into this particular expression of S1T. Okay. Here we know that because S2T is supposed to be 0. So the energy content will be 0. Okay. So that we don't need to calculate, but when AC equals to root over 2 EB TB, that will be for your binary bit equals to 1. So I can substitute this AC equals to this particular value into this expression. You will be getting this particular expression. Okay, you see this. So I have just taken out root EB out of this root. Okay, and a little modification I have done, and then we have got this particular expression root EB and root 2 upon TB. So I'm just keeping this root 2 upon TB here, multiplied with the cos 2 pi FCT, and then I am keeping this root EB outside this particular root. Now, what I am trying to rewrite this expression in this form of root EB multiplied with the phi 1t. Okay, so as I said that in the previous discussion of our signal space representation, I said that any signal that we are going to generate that will have a certain magnitude or amplitude multiplied with a particular basis function. Okay, I said that it should be multiplied with a certain basis function. So here you see that this S1t can be represented by writing in this way, like a root EB multiplied with the basis function phi 1t. Again, S2t can also be written as 0 multiplied with the root 2 upon TB cos 2 by FCT. Again, that can be written as 0 into phi 1t. Okay, because I have defined here phi 1t is our basis function root 2 upon TB cos 2 by FCT. So this is our basis function for this particular amplitude shift decaying. And now one thing that we have to prove here is that as we know that the property of the basis function is that the basis function should be a normalized function. Okay. So as we know that it should be an orthonormal function. So it should be orthogonal and as well as a normalized function. So because here orthogonality we cannot prove because we are just having a single basis function. Suppose if we would have like if we had two basis functions, then only we can get inner product and then we can prove that it is orthogonal. But here it cannot be proved like it is the orthogonal because it is just a single basis function. So we can go for the proving that this particular orthogonal, this particular basis function is a normalized function. So how it can be done? We can just integrate it over this duration of 0 to TB, and we can calculate phi 1t multiplied with the phi 1t dt. So you try to just work out this one. Okay. So once you will perform this, this is very simple to do. Okay. So once you will perform this, you are going to get this particular expression. Okay. Just to substitute for this phi 1t, and then you will be able to get this particular expression. So once you will do this, you will end up with this particular expression 1 upon TB multiplied with t plus sine 4 pi FCT divided by 4 pi FC. And here we have the limit 0 to TB. Now, if you want to get this to be like it should be a normalized function. You see this factor has to be 0. Okay, this has to be 0 once we substitute the limits. Okay, so obviously when substitute for 0, this entire term will become 0 because sine 0 is also 0. Okay, and if you substitute t equals to 0, it will be 0. But when you substitute t equals to capital TB, in that time this will become TB, and here it will be FC multiplied with the capital TB. Okay, so there is a requirement. You remember this requirement. It is very important point to be noted that this FC multiplied with the capital TB. Okay, this FC multiplied to be multiplied with the capital TB should give you an integer value. Okay, this FC multiplied with the capital TB. Once it is an integer value, here you can find that this going to be like uh, integer multiple of 4 pi. Okay, so it will be always like it may be 4 pi, it may be 8 pi. Okay, it may be like 12 pi. Okay, it may be 16 pi. So all for all these integer values, okay, if we coming out as an integer, this sign factor is going to be 0, and then that time this factor will be eliminated, and the result of this integration, we are going to get equals to unity. Okay, because here we are going to get TB and this will be 0, so the result that we are going to get is equals to unity. So this way actually we are going to prove that this basis function that we have taken with this condition, okay, is a normalized function. You remember that. So what does it mean by having FCTB equals to K? Okay, it means that if you see from this picture itself, you can see that within this TB duration, how many cycles that we have got in this particular duration TB. So you can see it is 1, 2, and 3. Okay, 3 complete cycles we have got. Okay. Similarly, again here you have, if you see within this TB duration, we have got the 3 particular cycles. So this FC multiplied with TB means within this duration of TB, the number of repetitions is actually an integer value. Okay, you remember that. It is a very important thing that we have to note down. It should be an integer multiple. Okay, it should be an integer value. Okay, so within this TB duration, the number of cycles that we have to got should be an integer value. So that we can calculate also. Okay, for example, if you want to get this TB, okay, so TB will be 1 upon K upon FC. Okay, so FC is the 1 upon FC will be giving the time period of this particular carrier. Okay, so K multiplied with the time period. So this bit duration TB should be some integer multiple of the time period of the carrier. Okay, so that we have to maintain to keep this as a normalized function. Okay, to keep this as a normalized function. So this is the thing that we have. So now we can see that we have these two signals S1T and S2T. Okay, there is a certain relationship between this FC and TB, which is an integer multiple. Okay, so now when we have these two signals, we can actually represent these two signals on our signal space representation. So here we can see that we actually have a certain only one basis function. Okay, only one basis function. So let us suppose that if I denote this basis function by a certain line. Okay, so let us say I have this line. Okay, and when I increase, if I draw a line like this, okay, and with arrow sign, it means that its magnitude is actually increasing towards this direction. Okay, so that will be representing our basis function phi 1t, and then at any certain point I can have the magnitude. Certain point it will have a magnitude equals to 0. Then at certain point I can tell that this magnitude is this much and that much. Okay, so that magnitude is actually increasing, and then again it is having a magnitude equals to negative values. Okay, so this way actually I can represent this by having a signal space representation. One more thing that we have to note down is that we are just having a only one basis function, and therefore it is a one-dimensional signal space. Okay, it will be a one-dimensional signal space. So here you can see that I have just denoted this particular signal space representation. I have just denoted this basis function by this particular line that represents the phi 1. And as I said that at certain points, it will be actually reflecting the magnitude of this particular basis function. For example, at this point, it may be having a zero amplitude, okay, and then when we go towards right, okay, its magnitude is actually increasing, okay, of this particular basis function. So even when we draw a coordinate axis, okay, if you remember, we are having x-axis and y-axis. So what does it mean that we are having a x-axis? Okay, we actually denote it by 1, 2, 3, 4. So basically, it is having a certain unit quantity, and that from that unit we are actually multiplying those factors 1, 2, 3. Okay, and then we are actually measuring anything. Okay, so similarly, again, here the unit quantity that we are going to take is 520, and then its magnitude is actually being depending on these factors. Okay, whatever we are going to multiply, that will become the magnitude of that particular basis function. So here we can see that we actually have the two different message points. Okay, now this m1 and m2 actually denotes the message points. Remember that it is called as the message points. So we are having two message points, so corresponding to binary bit 1, that message point, if you see, it is actually root eb. Okay, it is root eb times of 5 and t. So the same thing I can represent it here like root EB times 5 and t. Okay, so because this is a basis function, so here I can write this magnitude at this point of the basis function is root EB. That denotes our message point M1, and similarly over other message point M2 is 0 times the 5 and t. So here I have denoted it by the 0. So now these are the two different message points that we have. Okay, so you remember that basically when we try to recover back the original message informations, okay, after doing the demodulation, okay, what we generally do is we have to have a particular circuitry that will be able to make a decision whether the sent signal was binary bit 1 or it was a 0. Okay, you remember that whenever we are sending this type of carriers, okay, when it is traveling through the channel, a channel is going to be adding certain noises, and because of the presence of the noise in the channel, the amplitude of this carrier is going to be changed. Okay, sometimes it is increasing a lot, and sometimes it is also decreasing a lot. So though you are sending 0 at this present, means we are sending 0 for binary bit equals to 0, but it may be that there will be a certain amount of amplitude may appear at the output because of the presence of the noise. So that time we need to make a decision whether the sent information was corresponding to binary bit 1 or it was binary bit 0. So generally in between of these two message points, we need to have a decision boundary. Okay, so we need to have a decision boundary because while receiving the signal, exactly we are not going to get this amplitude root EB. Okay, we are not exactly going to get this root EB, but rather this magnitude is either less than root EB or it may be greater than root EB. Okay, depending on the type of channel and amount of noise that is being added. Okay, so it may be a certain variations, okay, around this message signal M1 or message point signal N1. Okay, there may be a certain means variations. So this will be our decision boundary in middle of this two. Okay, and there will be a certain region that will be treated. Okay, so anything this dashed line, okay, anything greater than this dashed line can be actually means regarded as message point M1. Okay, because this is our decision boundary. So let us say this value reflects like this decision boundary reflects root EB by 2. Okay, it is representing root EB by 2. So any magnitude of the message signal or yes, any magnitude you can say, or any energy of this particular basis function that we are going to receive, if it is greater than root EB by 2, okay, then it will be regarded as message point M1. Okay, similarly, if it is less than that, it will be regarded as message point M2. So therefore we are actually having two different reasons. Okay, this is for reason 1 for binary bit 1, so to make the decisions, and this is our region 2. Okay, so for our binary bit equals to 0, so this is for binary bit 1 and this is for binary bit 0. So entire for this magnitude, it will be means it is going up to infinity. You remember, okay? It is going up to infinity. Anything greater than root EB by 2 can be regarded as binary bit 1, and anything less than root EB by 2 can be 0. So that way, we actually make the decision while recovering back this particular message signals, okay? This type of modulation. So I hope you must be able to understand this. Okay, and this is very important discussion. You remember, we have the decision boundary, and then because of the presence of the noise, we will be having a certain reason, and within this reason, we have to make the decision whether it is corresponding to 1 or corresponding to 0. If let us say that the noise that we have added is too much, okay, and because of the very high noise, what will happen is that if we have sent the like pulse or the carrier corresponding to binary bit equals to 1, and if due to the presence of noise, if its magnitude is deteriorated, and then it is actually becoming less than root EB by 2. So that time what happens is this 1 will be actually treated as 0. Okay. So that time the receiver will say that means it will understand that the binary bit that was sent is equals to 0. And that time the error will occur. Okay. While receiving the signal, there will be an error. Okay. Similarly, if there are too much noise, and because we have sent 0, and if energy we have sent equals to 0, but while receiving, if it is greater than root EB by 2, that time this 0 will be regarded as 1, and that time the error is going to be occurred, okay, at the receiving end. And that is actually calculated by calculating the probability of error. So what is probability of error? So what is the probability that 0 will be treated as 1 at the receiver and 1 will be treated as 0? So that calculation we have to perform separately. So right now you just try to understand this one. So this is our signal space representation. Now we have to talk about what will be the bandwidth of this particular signal. Okay. So if you remember that we have already done the, we have calculated the Fourier transform for a rectangular pulse, okay, of duration PB. So if you remember, that was a sinc function. Okay. So that was a sinc function like this. So I have just taken the major lobe, though it is not looks like the sinc function, but you try to remember that I'm just trying to represent that it is a sinc function. Okay, you just try to understand that I have just taken the major lobe, and all other high frequency component I have neglected, because most of the power content is available within the major lobe. So if you remember that, that was the like bandwidth of our pulses. Okay, after removing the high frequency component, that bandwidth was actually 1 upon TB. Okay, so it is actually having this low frequency, significant low frequency component that is varying from 0 to 1 upon TB. So this is our message signal. Okay, this is our message signal, and it is going to be multiplied with the high frequency carrier. So once we multiplied with the high frequency carrier, obviously this spectrum is going to be shifted around frequency f equals to fc, and that we have already discussed so many times in our analog communication. Okay, so this way we are going to our get our frequency component. A similar frequency component you are going to get in the negative axis. You can also calculate these values. Okay, so basically, to calculate the approximate bandwidth of our ASK signal, okay, you can calculate this width. Okay, what will be the width over here? That will be equals to 2 upon TB. Okay, you can calculate this width. So that will be our bandwidth, approximated bandwidth of our ASK signal. So that will be equals to 2 upon TB, or you can also say that 1 upon TB is actually your bit rate. So 2 multiplied with the bit rate is giving you approximate bandwidth. Now you can have this demodulation part again. So here you can see that, if you see this, because I said that it is amplitude shifting. Okay, so you can see that this information is actually available in its amplitude part. Okay, so generally we can have the envelope detector also to detect such signals. Okay, but if you want to do it coherently, okay, if you want to make a coherent detection, okay, what we can have is we have to just apply this ASK signal with this particular signals S1T and S2T corresponding to bit 1 and bit 0. So this ASK signal will be directly applied to this particular product modulator. And as we know that to do this synchronous demodulation or coherent demodulation, we need to multiply the same carrier again Okay, and then we have to pass it through the low pass filter. Okay, so that will be passed through a low pass filter, and we have to multiply it AC cos 2 by FCT plus phi, and then obviously output of the product modulator will be the product of this two, and then we are going to get AC square cos phi plus cos 4 pi FCT. Because it is a low pass filter, this will be filtering out the high frequency component, and the output of the low pass filter that we are going to get is AC square by 2 cos phi. You remember that there is a phase offset that we have chosen at this particular end. Okay, so if there is a phase offset, obviously the masses signal is affected by the phase shift. If phi equals to 90°, we have already studied that there will be a quadrature effect and the masses signal is completely lost. So that phase coherence is actually required. Okay, you remember that in the synchronous modulation, demodulation. Okay, this phi should be equals to 0. And at least it should not be like equals to 90°. Otherwise, our mass signal will be lost. Okay, so this way the output that we are going to get is equals to AC square by 2 whenever our S1T is present. Whenever S2T is present, ideally the output is equals to 0. Okay, so this is a very crude way I have explained you how it is actually demodulated. Okay, but I will be explaining you how it is actually demodulated in actual circuits. Okay, it is a very crude way to say that it is means demodulated in this way. Okay, I will tell you how it is actually done, because we have to have a particular decision making devices. Okay, because here we have to distinguish between 0 and 1. Fine, so we need to have a decision making device. So try to understand another scheme like phase shift king. Okay, as I said that phase shift king, what we have to do is we have to again take the binary data. You note down that in the previous case we have taken the unipolar on off king signaling. Okay, on off signaling, right? Here we have to take the line code equals to polar non-return to 0. Okay, this is mandatory, you remember that. Okay, it is mandatory, we have to take like binary data that should be having a line code of polar NRZ. Okay, so this type of waveform we need to generate, and then we have to multiply the carrier AC cos 2 pi FCT, and then this type of waveform has to be generated. As I have already explained you, there will be a 180° phase reversal at this point whenever there is a 0 occurring. Okay, so this way we are going to get the uh, phase shift king output. So this is our phase shift king output. Okay, so similarly you can see that what will be the signals output. So corresponding to binary bit equals to 1. Okay, binary digit equals to 1. The signal S1T that we are going to get is root over EB, root over 2 upon TB cos 2 pi FCT. Again, I will be calling it as a basis function. So this can be written as S1T equals to root over EB phi 1T. Again, S2T can be a minus root over EV root over 2 upon TV cos 2 pi FCT for binary digit equals to 0. So this will be our output. Okay, S2T is minus root over EB phi 1T, and this is S1T root over EV phi 1T. Where phi 1T is our basis function we have already previously defined, which is equals to root over 2 upon TV cos 2 pi FCT. So now the same thing again, you can have this signal space representation. Okay, so here you can see that we have this basis function phi 1T. Here this message point, again we have the two more message points and only one basis function. So again we are going to have the one dimensional signal space representation. So this is our phi 1T, and onto this phi 1T we have to represent these two message points. We have to locate these two message points M1 and M2. Okay, so this is our M1, which is equals to root over EB, and here it is minus root over EB. Okay, so these are the two message points. Fine, and now this has to be for example, you can see that you can calculate what will be the difference between these 2 points. So that will be equals to 2 over root EB. Okay, so again we are having, this is our decision boundary. Okay, this is our decision boundary, the midpoint of these two message points. And then after this decision boundary, okay, any value greater than this decision boundary, obviously the decision boundary will come at equals to 0. Okay, so any magnitude greater than 0 will be treated as binary bit equals to 1. Okay, and any magnitude less than 0 will be treated as equals to binary bit equals to 0. This way we have to actually make the decision. So again, if you want to demodulate, you have to apply the same signal. Okay, you have to multiply it with the same carrier, AC cos 2 pi fct plus phi. Okay, so obviously, if you do this analysis, you will find that after the low pass filter, the output that we are supposed to get is AC square by 2 cos phi, and corresponding to binary bit equals to 1, and it will be minus AC square by 2 cos phi, corresponding to binary bit equals to 0. Okay, again you are going to get the same approximate bandwidth of the PSK, and that will be 2 upon TB. Okay, you can calculate it because nothing has changed. Okay, so again we are having the same rectangular pulse which is going to be multiplied with the very high frequency carrier. So again, its spectrum is going to be shifted. Okay, so that way approximated bandwidth will be remain same, that will be equals to 2 times the bit rate. Now uh, you remember that because here the information that we are taking is only binary bits. Okay, single binary bits we are using. Okay, its name is also called as like binary phase shift keying. Okay, BPSK. Okay, either you can call it as PSK phase shift keying simply, or you can also say that binary phase shift keying. The meaning is for the one binary bit, okay, corresponding to 1 and 0, the phase of the carrier is going to be changed. Okay, it is going to be changed. Now you try to understand a little bit a practical version of it. Okay, I have explained you this means transmitter part and receiver part. Okay, but if you see in the books, what you will find is that this type of diagram you will find. Okay, like over the PSK transmitter. So here it is the binary data sequence that we are going to get from the encoder, and then this encoder output will be applied to a polar non-return to zero level encoder. Okay, again means it is a line coding. Okay, and I have directly used the polar non-return to zero signal. So here this binary sequence will be applied to this, and then a polar non-return to zero signal will be actually generated, and this will be actually applied to a product modulator. And here the signal that we are actually applying to the product modulator is our basis function. Okay, whatever the basis function phi 1t that I have written, that has to be applied. Instead of applying AC cos 2 pi fct, we are actually applying this root over 2 upon tb cos 2 pi fct. So this is going to generate a binary PSK signal. Now this signal to demodulate at the runs at the receiver end, this signal has to be applied to the product modulator, and through this product modulator, again we have to apply the signal that will be our basis function phi 1t. Okay, so if you remember in the previous two slides, I explained you about the geometrical representation of the signal, and if you remember the analysis part, okay, I told you that if you want to get back the amplitude part of any basis function, we have to multiply it with the same basis function, and then again we have to go for the integration. Okay, so product modulator followed by an integrator, okay, of this kind is actually called as the correlator. Okay, it is actually called as the correlator. So you try to do the same thing. We have actually, for example, if we have sent S1T, so once we have sent the S1T, for S1T corresponding to S1T, what we have done is we have to multiply the same basis function phi 1t, and then we have to do the integration. So I'm just trying to do this. Okay, 0 to tb root over eb, so it is root over eb multiplied with the phi 1t, then again phi 1t, this phi 1t. Okay, so then dt, so basically this is coming out as root 2 over eb 0 to tb phi 1t multiplied with the phi 1t dt. Okay, I have already proved that this 0 to tb phi 1t is going to give you value equals to 1, because this basis function is nothing but our normalized function. So this integration is going to be equals to 1. So this output 0 to tb s1t phi 1t, okay, that our your correlator gives. Okay, you see this correlator output. Okay, so this block diagram is actually I'm representing with this mathematical expression, and this output is supposed to be root over eb. Okay, so this is the means output of this correlator that we are going to get, and then there will be a decision making device that will be actually comparing this output, okay, with a pre uh, threshold. Okay, there will be a predefined threshold. So based on the threshold, because here the threshold value is equals to 0, you can see that the decision boundary that we have taken, that will be equals to 0, because here it is symmetrically situated around 0. Fine, because it is a root eb and here it is minus. So this will be our means predefined threshold. So whenever this value that will come out after the correlator, if it is greater than threshold, it will be chosen as 1. Okay, whenever it is less than 1, it will be chosen as equals to 0. So this way actually we receive our signal at the receiver end. So, based on this discussion, you try to understand that which particular block diagram you have to choose. If you are means discussing with this particular block diagram, you have to explicitly explain this way, or if you are taking this one, okay, you have to explicitly define this way. Okay. So I hope this discussion must be you are must be able to follow. If you have any further doubts or query, you let me know with your comments. Okay, I will be discussing it further. So I will stop here for today. I will be discussing the next topic in the next lecture. So please thank you for watching this video. So for more update, please stay connected with the channel. Thank you for watching this video.